Okay, Assalamualaikum warahmatullahi wabarakatuh, and very good day to all of you. So for part 3, chapter number 3, which is about the cascade performance. So for this part, we will discuss about the compressor cascade profile losses, where we will learn about the effect of blade losses in terms of what I call the compressor efficiency determination. Okay, compressor cascade losses, which is focused on the blade losses. So according to the Howell 1945, blade losses need to be considered for the compressor blade roll efficiency calculation. So as we know, efficiency of a compressor cascade, as shown in the photo, can be determined by using numbers of equation. One of the equation is by using I call the compressor cascade efficiency mu d equal to 1 minus 2 cd cosecant alpha m divided by cl. Okay, for optimum condition, we can calculate the maximum efficiency for a specific condition by using the second equation, where mu d maximum equal to 1 minus 2 cd divided by cl. So in both equations, we have CD terms, where CD terms can be obtained by using the formula for drag coefficient, where CD also equal to drag coefficient, profile drag coefficient CDP equal to D divided by half rho cm square multiplied by chord length. And this CDP equation actually only consider blade profile losses. So as we know, we have 4 types of blade losses. First, blade profile losses. Second, annulus losses. The third one is secondary losses, and the final one is the fluid leakage losses. But for CDP formula, the formula only consider the blade profile losses. So now Howell will investigate, try to determine efficiency of a complete compressor stage by considering the other type of losses. Okay, a compressor stage actually consists of 2 parts. First part referred as stator, static parts, and the second part referred as rotor, which is dynamic parts. So the Howell will consider the efficiency of the compressor stage by considering other type of blade losses, such as annulus loss, where we can determine the annulus loss by using this formula CDA, okay, which is equal to 0.02 S over H. S is blade pitch or spacing distance, and H refers to the blade length or blade height. And the other blade losses that considered by Howell is the secondary losses, where we can determine by using this formula CDS equal to 0.018 CL square, where CL equal to leaf coefficient. Okay, according to the suggestion that suggested by Howell 1945, where we need to consider other type of blade losses. So we know that we have 4 type of blade losses: profile losses, annulus losses, secondary losses, and the last one we have leakage losses. So in Howell investigation, Howell only consider profile losses, annulus losses, and also secondary losses. So I want to ask you, why in the cascade blade investigation conducted by Howell doesn't consider the leakage losses, the final type of blade losses? So why in the cascade blade investigation the leakage losses is not considered by Howell? Okay, I will give you 5 seconds to think about it. Okay, one of the reason, because both ends of the cascade blade were fixed to the transparent material surface in the test section of the cascade blade, where no clearance to allow tip leakage from occur, as shown in the figure. So the photo shows the two identical cascade blade. So normally these blades in cascade blade investigation will attach to what we call the transparent material surface at the both end of the cascade blade, as shown in the figures. And we can see that both end of the cascade blade are fixed to clear material surface. So if we look by looking at the front view of the cascade blade arrangement, so we can see that both end of the cascade blade fixed to the clear material surface, which is no gap for fluid leakage occur during the cascade blade investigation. So for this case, we will not have the losses, what we call the blade losses due to fluid leakage losses. Okay, unless we change the arrangement of the cascade blade test conditions, such as we consider a gap in the cascade blade test section in a wind tunnel. For example, we have only one what we call a transfer material surface that fixed at the end of the cascade blade. Okay, so we only have one end is fixed to the clear material surface, and the other side we provide a gap, as shown in the figures, where we allow fluid leakage at the tip of the cascade blade. Okay, if you refer to the front view, so we can obtain one side of the cascade blade without gap, and the other side will have a gap that will allow the fluid flow throughout the gap and produce fluid leakage losses at the tip of the cascade blade. However, this condition is not considered in Howell study. That's why in Howell investigation, he will not consider leakage losses for his what we call compressor cascade blade investigation. So Howell will consider only profile losses, annual losses, and also secondary losses. So that's why no need to consider tip leakage losses in the investigation. Okay, losses in a compressor stage by Howell 1942. So Howell conduct an experiment to obtain the result in terms of the variation of stage efficiency with flow coefficient, where Howell consider various types of blade losses, such as blade profile losses, annulus losses, and also the secondary losses. So this is the result that obtained in terms of graph by Howell 1942, where he obtained the losses in the compressor stage, where the graph will shows the relationship between stage efficiency and also flow coefficient, with considering different type of blade losses. So flow coefficient refer to psi in terms of symbol equal to Cx over U. So the parameter of flow coefficient consists of U, which is represent the symbol for blade speed, and Cx represent the parameter for axial flow velocity. Okay, so in the graph we have the first important line or condition that we refer to is the design condition or design line. So the design normally refer to the best condition in order to obtain the basic criteria for the design point, which is the optimum efficiency, the condition with optimum efficiency, minimum losses, and also the condition that we already consider few value of safety factor. And this we already discussed when we discussed about the result that obtained by Howell in terms of deflection angle, incident angle, and also total pressure loss coefficient value. So the second important condition or line we call surge line. So in order to understand the meaning of surge or surging phenomena, we need to consider a compressor map, or we consider other name of the for the compressor map if is the called the compressor characteristic graph or performance maps for the compressor. So the graph will consist of the in terms of data, in terms of pressure ratio P2 divided by P1 for the compressor, mass flow rate, and also the numbers of curve in terms of rotational speed curve on the graph. Okay, N stand for rotational speed. So normally the unit for rotational speed is RPM, revolution per minute. So we have numbers of N constant curve on the graph, and we have two limitation line. First limitation line we call choke line. Later on we will explain about the choking phenomena, but for this slide we will explain about the second limitation line that refer as surge line. So we will have this line due to the surging phenomena that occur in the compressor. So if you look to the N constant curve, if we reduce mass flow rate, as we can see in the graph, the value of pressure ratio will increase. So that's good for the compressor condition. However, at certain point, if we decrease more mass flow rate, so the value of pressure ratio will not increase or decrease. So no effect to the pressure ratio if we change the value of mass flow rate. Okay, for normal condition, if we reduce mass flow rate, the pressure ratio of the compressor will increase. But at certain point, the mass flow rate will not affect the pressure ratio that obtained by the compressor. So this point we refer as surge point. In terms of mechanism in this surging phenomena, so we look at this figure. So this figure shows an example. We have two identical compressor blade for a rotor. So we have a fluid flow into the rotor with C1 velocity and come out from the rotor with C2 velocity. So we have inlet pressure P1 and also outlet pressure P2. Okay, so in order to operate the compressor, so the rotor must rotate, and then the fluid flow will the fluid will enter the compressor rotor, will flow through the compressor rotor. Okay, when fluid flow through the compressor rotor, the pressure ratio will increase. So the pressure ratio of the compressor will increase due to the compression process. And then we allow more fluid flow through the compressor rotor, so we will get we call the high value of pressure ratio. So at high pressure ratio condition, where we refer as the surge point, so reverse flow will occur during the condition, and when reverse flow occur, the outlet pressure will reduce. So the outlet pressure of the compressor will reduce. So because we already set for the compressor in terms of parameter to obtain certain value of pressure ratio, so the compressor will make compensation process where the compressor try to re-increase the pressure so that the pressure difference will be increased and achieve what called the value that we set during the compressor operation, for the compressor operation. So now for the compensation process, the compressor will allow more amount of fluid flow throughout the compressor rotor. So this will cause the reverse the different direction of fluid flow in due to the fluid flow enter the compressor rotor, and the second one is the fluid direction out from the compressor rotor due to the reverse flow. Okay, so this will cause a certain phenomena, a certain effect due to the surging phenomena, where we will have pulsation of airflow due to the different direction of fluid flow in the rotor. And also this also will cause mechanical vibration and also the increase of noise level during the operation. So we need to prevent surging phenomena from occur during the compression operation. So in order to prevent, we need to change the compressor condition so that the condition of the compressor not enter the called surge limit line. Okay, so that is the explanation of the surging phenomena in the compressor. Okay, so the surge line in the graph is refer to the phenomena that I already explained just now. Okay, so let's go back to the result that obtained by Howell 1942 in terms of stage efficiency for various value of flow coefficient. So first graph that obtained by Howell is the graph of stage efficiency by considering only annulus loss. Okay, that represented by blue color curve. And if you compare to the ideal value of stage efficiency, which is 100%, so the stage efficiency that obtained when we consider annulus loss will have reduction of efficiency at design condition around 2.2%. Okay, so if you ask the working range at that condition, so probably the working range we can choose start from the design point, which is flow coefficient equal to 0.96 up to around 1.1 in terms of value of flow coefficient. Okay, so further, when we consider more type of losses such as annulus plus secondary losses, we will have what we call the second result for stage efficiency that represent by green color line, and the reduction of stage efficiency we will have additional reduction of stage efficiency around 4.4%. And when if we want to determine the working range at that condition, we can choose start from the design point 0.96 in terms of flow coefficient until 1.3. Okay, the third line represent the stage efficiency curve when we consider three types of losses such as annulus, secondary, and also profile losses. So we have different shape of stage efficiency curve for this case that represent by pink color curve. Okay, if we include more type of blade losses, so we'll get what I call lower value of stage efficiency in the result of the cascade blade. So for the third case, if you were asked by somebody about the working range, you can decide from the design point up to 1.03 in terms of flow coefficient value. Okay. Example 3.6. In the actual operating condition of a compressor stage, various types of losses need to be considered. Figure shows the variation of stage efficiency with flow coefficient for different combination of losses. It is found that the compressor stage experience surging phenomena when blade speed and axial flow are at 100 meter per second and 80 meter per second respectively. After considering the surging point, flow coefficient at design point for the compressor stage is 20% higher than the flow coefficient value at the surging point. Determine the compressor stage efficiency at the design point when considering different type of losses. Okay, so this is the question for example 3.6, and the figure of stage efficiency also provided in the example. So you need to use this figure to determine to answer the question. Okay, solution for example 3.6. So data given in terms of blade speed blade speed equal to 100 meter per second, Cx equal to 80 meter per second. Flow coefficient for surging condition you can determine by using the flow coefficient formula, where psi s equal to Cx over u. By referring to the data given, psi s equal to 80 divided by 100, which is equal to 0.8. Flow coefficient for design condition, as mentioned in the question, is equal to 20% higher than flow coefficient at surging condition. So manipulating the value that you already calculate for flow coefficient at surging condition. So flow coefficient for design condition, psi d equal to psi s plus 0.2 multiplied by psi s, equal to 0.96. So by referring to the graph, draw a vertical line for design flow coefficient as shown in the figures. So stage efficiency at different losses condition can be determined from the intersection point between vertical line for design flow coefficient and also the stage efficiency curve. Okay, so for the what I call the stage efficiency, when we just consider annulus loss, just find the intersection point. So we will get stage efficiency at the condition is equal to 97.9%. If we consider annulus plus secondary losses, we will get stage efficiency, lower stage efficiency, which is at 93.6%. And the last one is stage efficiency when we consider annulus plus secondary plus profile losses. So we'll get the stage efficiency of the compressor equal to 89.6%. Okay, in order to test your understanding for chapter number 3, part 3, please answer the question. So first question, why do we need to consider various type of blade losses in compressor efficiency calculation? Question number 2, give the basic criteria for the design condition. Number 3, is it possible to choose the operation condition higher than a design point but still below the surging condition? Give your reason. So you have to answer the question by clicking the link provided in my blog. Remember that you need to know the password in order to open the link. The password was given throughout the video related to this topic. The clue is also given in the link. Okay, that's all for part number 3, chapter number 3. Assalamualaikum.